Okay, so in radian, right? So I wrote up the first expression. So exponential function of minus zeta omega n pi over omega bracket by, so pi, cos of pi is equal to minus, okay, so this is minus C1 plus by 0, and this is plus XSS. So we know that this expression will give us, this will be equal to minus C1 E minus zeta omega n over omega pi plus by XSS. Okay. So we already know, okay, a known based on when x is equal to 0, time is equal to 0, C1 is equal to minus XSS. We found that already. Okay. So when that's the case, our overshoot or the function will now look like this. Okay. So this will be equal to XSS exponential of minus zeta omega n over omega pi plus by XSS. So this portion over here, this portion over here is known as our overshoot. Okay, that portion is our overshoot. So by looking at this function, okay, we realize that this is coming back to this diagram over here. So I'm going to draw the arrow now. So this expression over here is our XSS E minus zeta omega n over omega multiplied by pi. Okay. So we also know, I'll let you guys write this out first. So we also know, right? So our overshoot is equal to XXS, okay, exponential of minus zeta omega n over omega multiplied by pi. Okay, just the overshoot function. Whereas the equation above is x at pi over omega. Just the overshoot portion, it is E minus zeta omega n over omega times pi. And we already derived that omega, knowing that omega is equal to, we just derive it, omega n over 1 minus zeta squared, right? We derived this earlier. So by knowing that, therefore, the overshoot will be equal to XSS. Eugene, come on. Exponential of minus zeta, okay, omega n over omega n square root of 1 minus zeta squared multiplied by pi. So the final form of the equation is XXS exponential of minus zeta pi divided by square root 1 minus zeta squared. So to calculate the percentage of overshoot, Okay, sometimes you might be asked. So this will be equal to XSS. Okay. Exponential minus zeta pi square root of 1 minus zeta squared and divide by XSS multiplied by 100%. Okay. So you can get rid of this. So you just have E minus zeta pi square root of 1 over square root of 1 minus zeta squared. Okay. And then there's a relationship. Okay. So I'm going to write on a table. Anyone have questions so far? Okay, just a few. Yes. Can you see when it's like this? Is it better now or no? That's better. Okay, so I'll write based on this. Tell me earlier, okay? Don't suffer on your own like this. Right. So now I'm going to write a table. I'm going to create a table where this table will have damping ratio, which is our zeta. Okay. And then we have our percentage overshoot. Okay. And if our damping ratio is 0.2, right? 0.4, 0.6, and 0.8, what will happen is our overshoot is 52.7%, 25.4%, 9.5%, and 1.5%. So as you can see, if our damping ratio is very small, our overshoot tends to be very what? High. Okay. Yes.
What is the percent shoot actually?
So the percentage overshoot is the overshoot divided by the steady state multiplied by 100. Right? So that's the percentage of overshoot. So what I just done is I just put the zeta value into here and calculate it.
Right. But like on the actual graph versus omega t, what does the percent overshoot represent here?
So it's just a percentage. Okay, it's just a percent. So okay, good question. Okay, I'll give you an example. Let's say, okay, it is the portion of the overshoot relative to the steady state value. That's it. Okay. If this value over here is 100, the overshoot is 50%. The overshoot will be what? There you go. Now, why is so important to know about this overshoot? I'll give you a very realistic example now. So in terms of stress, okay, for example, at this stage, at 100%, we are at your stress Y. Stress Y is over here correspond to our U stress. Okay. So U stress over here is equal to P applied divided by area. Okay. So let's say this is based on static analysis approach. Okay. Now your system goes through what? A dynamic system. Okay, now your structure is not just force divided by area, but it goes through a vibration and oscillation. So now if the oscillation is 150 or 50%, now the P applied increased by what? 1.5%. Divide by your cross-sectional area. Now this stress is known as your stress peak. Okay, that is your stress peak. So we are very sure that your stress yield is going to be less than your stress what? Peak. Okay, so that's where when we design structure, okay, 2 P04, we take everything as what? Static. Nothing is moving. Okay. Now, if we were to induce a dynamic system into it, okay, what will happen now? Your stresses will what? Increase. And the way to reduce this stress is by doing what? By putting a what? A damper. Right? So, I mean, not in Canada, we don't get a lot of earthquake, but countries in Japan, they have what? Earthquake. So under the building, they also have a what? Spring damper system. The spring damper system helps them in what? Controlling the what? Overshoot. Can you see the link now? Right? It gets more. So I would recommend you all to watch any Discovery Channel regarding building bridges where you have earthquake. It is amazing. It's crazy. Yes. Say it again. Okay. The spring is to pull the building back. Right? If Come down. It's the earthquake, right? There's no spring. I just wish you would just go on and on. Right? So can you come out? You are my spring and damper. Spring and damper, you have to relax when I push here. Okay. When I say left, you go right. When I say right, you go left. Why do you say that? If that's what? The law. The spring and damper force will always oppose to the what? Right force. Okay. So I'm going to go left, you're going to go where? Okay. So what will happen? So I push him left, you go away. And if I go right, yeah, that's not very bad. He goes one way, okay? So when I push him, right, he will push in the opposite direction, so he's not leading. Without the spring and damper, then you get the spring and damper, if I push you, you will keep on going. Or the deflection will be higher, right? Deflection, sorry, you're not moving, your deflection will be higher. There's nothing to absorb the energy but except what? You. That's not because very comfortable, right? Yes. Good question. Okay, now you understand it.
Well, I have another.
Later you tell me. Yeah, this is my show. Later tell me. Okay. Very good question. Why we have it? You cannot just have, I mean, sorry. Your question is also why not I just have the damper only? Right? If I just have the damper only, it will close and eventually the damper will fail. Right? It just slow the speed down, it dissipates the energy, but I need it